This question is from GATE 2021 Mechanical Engineering Paper Set 2, question number 34. Consider the system shown in the figure. A rope goes over a pulley, a mass M is hanging from the rope. A spring of stiffness K is attached at one end of the rope. Assume rope is inextensible, massless, and there is no slip between the pulley and the rope. The pulley radius is R and its mass moment of inertia is J. Assume that the mass is vibrating harmonically about its static equilibrium position. The natural frequency of the system is dash. Let's find out. Now here we can see that degree of freedom of this system is theta, because when the pulley rotates with angle theta, a point on the circumference of the pulley, if let's say P is a point, it will shift to a new position. Let that position be P dash. So when this pulley rotates with angle theta, the mass is going to move downwards if we assume that the rotation is clockwise. Let this downward movement of the mass be y. So y can be given as length of this arc, which is r into theta. Similarly, extension of the spring will be x, and that will also be equal to r into theta. To find the natural frequency of this system, we will use the formula under root of K equivalent upon M equivalent, that is stiffness equivalent upon mass equivalent. Because mass is not concentrated at the point where displacement takes place. Therefore, both the quantities will be not directly available to plug into this formula, but will have the stiffness and mass equivalents. And these will be obtained from the equation of motion, which will be of the form M equivalent theta double dot plus K equivalent theta equal to 0. Damping and external force both are 0 in this case. To formulate this equation of motion, we will use the Lagrange formulation, which says derivative of dou L by dou theta dot with respect to time minus dou L by dou theta is equal to 0, where Lagrange L is equal to kinetic energy minus potential energy. Now, to find out kinetic energy and potential energy of the system, we'll have to find kinetic and potential energies of each of the parts. So we have the parts, number 1 is spring, number 2 this pulley, and number 3 the mass. So for spring we have kinetic energy of the spring will be 0, because it only stores energy by virtue of its configuration in the form of potential energy. That potential energy will be given as half into stiffness K into its deformation x square of it. X can be written as r theta, I've already explained. So this will be equal to K r square theta square by 2. Second thing, for the pulley we will have potential energy will be 0, because rope is given to be massless, as well as pulley mass is not mentioned to us. So we can write its potential energy is 0, while its kinetic energy will be equal to half into mass moment of inertia J into angular velocity omega square of it. Angular velocity of the pulley can be written as theta dot. So we have J theta dot square by 2. Third one, for the mass we will have, again potential energy will be 0, because if we take this as the datum from where its displacement takes place, then its potential energy is 0. We can assume that center of mass is at the datum, and amplitude of vibrations is also small. Kinetic energy, however, will be given as half into mass into its velocity square. Velocity can be written as y dot, because displacement is y square of it. Now y can be written as r theta. So we substitute it here. We have m into r square theta dot square by 2. So this Lagrange can be written as L is equal to mr theta dot square by 2 plus j theta dot square by 2 minus kr square theta square by 2. Formulating the equation of motion, we will have time derivative of dou L by dou theta dot. So this will be applicable only to the first term. Last term does not contain theta dot. Derivative of this term with respect to theta dot will be 2 times mr theta dot by 2. So we have mr theta dot plus derivative of the second term will be 2 times j theta dot by 2. So we have j theta dot minus derivative of Lagrange with respect to theta will consist of only the third term because only the third term contains theta. Also, we have a minus sign inside this. So we have 2 times kr square theta by 2, that is kr square theta is equal to 0. So final equation of motion can be written as mr plus j. We have taken theta dot common and then taken the time derivative. So it will be theta double dot plus kr square theta equal to 0. We have the stiffness and mass equivalent terms here. So this is the mass equivalent term and this is the stiffness equivalent term. Substituting it here, we have natural frequency is equal to under root of kr square upon mr square. So actually here it is square. Sorry that I have missed the square here. So it is mr square theta dot here and mr square over here. So we have in the final answer, in the denominator, it is mr square plus j. Let's go back and mark this option. The answer that we found out is in option C. To learn more about vibration models, you can refer to the NPTEL video, Module 2, Lecture 1, Vibration Model, Equation of Motion, Natural Frequency. It's from the course Mechanical Vibrations. The course is taught by Professor Rajiv Tiwari. He is from Department of Mechanical Engineering of IIT Guwahati. I hope this solution helps you clear your doubt. Thank you.